Thank you. Yeah, and thanks again for inviting me here, and I hope we can have some nice discussions. So I'm going to present some joint work with my co-authors, Yannis Pascalidis here at BU, and my student, Arten Spiridonov, and my former postdoc, Shipu. To kind of loosely motivate what my work and the work of many other people in this whole strand of literature is trying to do, let me start with the figure. And by the way, you can all see my cursor, yes?
Yeah, I can the small cursor. Yes, I can see that.
Okay, because I use it as a pointer. So this is a figure, I took it from one of the OpenAI blog posts. On the x-axis is the year. Every dot kind of corresponds to a particular paper that beats some benchmark in machine learning. You may have heard of AlphaGo and AlphaZero. Some of the others did not receive as wide press as those two. And on the y-axis is basically the training time, the total training flops that it took to train the model. And the y-axis here is log scale, as you can see. And it's a line, right? So to show, basically the point is that the growth is exponential. People are getting better and better results on a variety of different benchmarks. But they're doing this by training larger and larger models, and they're training them for longer and longer and longer. And that there is a sense that this kind of thing cannot continue indefinitely, right? Exponentially growing curves have to stop growing exponentially at some point. But, you know, in the sort of 5 years here between 2013 and 2018, there was a roughly 300,000 times increase. Moore's law, to some extent, is still working in this field because people are building generalized, rather specialized hardware specifically for these applications. And that is what is in part fueling the exponential growth. But again, that can't really last forever. So I'm going to talk about one way in which we can really try to make, to throw more compute at this problem using distributed optimization, which is something that many people have been working on over the past few decades, even before these sorts of problems arose. So let me start with kind of a simple model for how we're going to try to parallelize the kind of training problems that are involved in these applications. So this model is in some sense a little bit simplistic, but not overly so. So we're going to try to solve an optimization problem in a distributed way. And what this means in this particular context is that you're going to have nodes in the network, and the ith node is going to have a bunch of data, okay? And this data usually comes in pairs, you know, xk, yk, where xk are features and yk are labels, like 0, 1. And the goal is to basically learn a predictive model, h theta, which basically has the property that it assigns to the label it assigns to each of the xk at any node is approximately equal to the corresponding yk. And so typically the theta is the parameter of the model. You have this predictor h and you parameterize it using some parameters theta. And the goal is to find the best theta that ensures that this is happening, find the theta that ensures h theta of xk is approximately equal to yk. And what you do is you usually define some kind of loss function on the y space. And okay, the losses generally tend to be application dependent. Here we're going to say, okay, we're going to define fi of theta to be basically the loss suffered using this function L, whatever it is, the loss function, the loss suffered by the predictor with parameter theta on the data stored at node I. Okay, so the sum here in the definition of fi as theta, the sum is taken over just the data at node I. And then you're going to go through all these data points and you're going to look at the loss between the actual label and whatever your predictor predicts. And then your goal is to find a minimizer of the sum of these functions. Okay, so the goal is to find a theta that matches all the data throughout the network. Okay, at every single node. So this is kind of like a sum of all nodes. And this becomes kind of a distributed problem. So this function capital F defined here is a network-wide global function, okay, in the sense that it depends on everything throughout the network. It depends on every single data point. But the way this physically works is that the ith node in the network has this data set script xi, so in particular, it has this function fi of theta. And except I, no other node knows fi of theta. I is the only node that knows fi of theta. And what can nodes do? Typically, you say something like, at every step, these nodes can start computing gradients or subgradients of these local functions, fi. They can exchange some messages with their neighbors, and so forth. And so the question is, okay, using this kind of distributed type updates where nodes are just taking gradients of their own functions and exchanging a few messages with their neighbors, how do you compute a minimizer of the function capital F, which depends on everything throughout the network? What sort of complexity estimates can you get, and what kind of performance can you get in real life? Okay, that's kind of very rough summary of how we're going to formalize this. How is this, maybe I should say this, how is this done in practice, right? So this is the kind of problem that many people face whenever you need to train a neural network or do anything else, and you have a model that is large enough that it can't be stored on a single GPU or a single CPU. What do people usually do? Well, the answer is that in practice, people usually use the star graph. What I mean by that is that typically when you train a model, everything will be within a single cluster. And you're going to have a whole bunch of workers. These are the leaves of the graph. And they're going to be coordinated by a server. That's what we call the node in the middle. And the way this is going to happen is they'll just go in rounds. So the server will say, okay, I think theta t is a good set of weights. So the server will take this theta t and it'll send it to all the workers, and all the workers will just compute all the gradients. So the ith worker knows the ith function fi, and it'll compute the gradient of fi at theta t, possibly corrupted by some noise, which I denote by w's. Then after that, the server at the middle, okay, so the workers are going to compute these gradients, possibly with noise. They're going to send them to the server, and then the server is just going to average them and do a gradient descent step. Then it's going to say, okay, now I have theta t plus 1, and they're going to repeat the same process. Okay, so the next time step, the server says, okay, here's theta t plus 1. Workers compute all their local gradients, send it back, etc., etc., etc. And this is what people do in practice. And it's reasonably good for many of the current applications, but it doesn't work as you try to scale things up. The reason it doesn't work is that in many of the kind of state-of-the-art, in many of the methods that achieve the state-of-the-art, the gradients are extremely large, and the iterates are also extremely large. So for example, people are training neural networks with 200 billion weights. Okay, so for example, one of the GPT-3 models that achieved some press recently had 175 billion weights. So every weight is typically a 64-bit number. So that basically translates to what? Something like 10 trillion bits. And let's say you want to parallelize this to not just 5 workers or 10 workers or 20 workers, but you want to parallelize this to 1,000 workers. So that means that every iteration of this, like step 2, at step 2, the server in the middle needs to receive 10 to the 16 bits. So that's a lot. And so the way people usually say this is they say, well, if you try to do this, there'll be a bottleneck in the middle. And it's not, and that bottleneck is going to dominate the performance of your method. Basically, it's hard to put enough wires to send 10 to the 16 bits. Okay, normally something like that does not exist. There are a number of approaches to dealing with this. I'm going to talk about one, but it's not the only one. So for example, one thing that people do that I'm not going to discuss at all is they say, well, what if you take gradient descent and then you compress the gradients? Okay, so maybe you don't need to send like the full 64 bits for every weight. And maybe you can even just not even send the full gradient. Maybe you can just pick several coordinates, et cetera, et cetera. So you can use that to kind of reduce the dimensionality of the problem somewhat. Here I'm going to describe a complementary approach to try to fix this. And I'm going to say, let's try to do this kind of problem over a setup where there's no bottlenecks. So something like this. Okay, so here in this kind of network, it's not like the star graph where everybody has to send to one node. You can have a whole bunch of nodes, but keep the degree bounded by some constant, or perhaps growing more slowly than order of n, like it is with a star graph. So the goal is to take something very basic like gradient descent and to try to make it work in this particular setting, where the nodes are these processors or GPUs, and they can communicate only with their neighbors in the graph. Okay, well, we're going to take kind of the simplest possible model that you can ask in this setting. We're going to say that computation is going to proceed in rounds, round 1, round 2, round 3. And at every step, the nodes can broadcast some kind of message to their neighbors, and they can compute a gradient of their local functions, or subgradient, or perhaps something that is corrupted by noise. Okay, so because very often the subgradient and gradient computations have noise in them due to the way they're done. I can go into that if needed. And maybe you want to add some additional things like maybe transmissions, links have delays, maybe messages can be lost, maybe nodes could act asynchronously, like you don't have computation in rounds, some nodes skip around and so forth. So you can think about more complex versions of these problems that try to incorporate some realistic network effects. Okay, but the objective is the same, right? So we have this situation where you have function fi at node I. We have the function capital F, which averages them, goes to minimize capital F. I'm going to assume, just for simplicity in this set of slides, that every fi maps R to R. That's not really necessary for any of the results I'll present, but it simplifies the presentation a lot. So I'm going to go ahead and assume that. Okay. So these kinds of problems go back a long time. So there's a book by Tsitsiklis, Bertsikas, and Athens in a corresponding paper in the mid-80s. Arguably, I can list some papers on that had similar flavor dating back to the 1970s. I think one name that comes to mind is Vivek Borkar, and Dmitry Bertsikas wrote a number of works in these veins. This particular formulation that I'm describing, this exact formulation where you have to minimize a sum of functions where every node knows one of the functions, that dates back not that long ago, only to about 2009, and so forth. Kind of over the past decade and a half, research on this subject has really exploded, in part because people were very interested in building sensor networks that act locally, act only based on local information. I'm not really going to discuss the previous work in a lot of detail because there's just so much of it. I'm going to focus on my main concerns, which is how to get these methods to work fast and, most importantly, give us a speed up, right? Because from my point of view, the main reason we're doing all this distributed stuff is so we can throw more computational power at these machine learning problems. And much of the existing theory does not always give a speed up when you do solve problems in a distributed way. And in this talk, I'm kind of going to discuss when you can and when you can't get the speed up. Okay. Right, and I guess that's what I'm saying in my last bullet point. I want to design methods that benefit from this kind of parallelization. Okay, so let me start by just telling you the very first result in the field. I'm going to kind of give a survey of sort of what is known and what kind of results are available. Just from my point of view, kind of hyper-focusing on one bit that is very important to the kind of results that I'm interested in. Again, here, this is going to start getting more technical, so feel free to interrupt here, especially just because, okay, if I'm assuming you know something that's not actually common knowledge, please speak up. So what the very first paper that introduced this did is they suggested how the first question that was asked is how do you take a subgradient method, which is kind of very basic and simple and something we all start our classes with. How do you take something like a subgradient method and you generalize it to work in this sort of distributed setup that I've described? And what they proposed is this very simple idea, which works so nicely, which works so beautifully, in part because of its simplicity. So they say, okay, so you have a network. So node I is going to maintain a variable which we're going to call theta I of t. And that variable is going to be updated in the way that's shown in this equation. So it's going to be updated to the next time step t plus 1 by taking a convex combination of theta j of t, where j is a neighbor of I. And these aij's, they're non-negative coefficients that add up to 1. Okay, so they're actually, I forgot to say that they're non-negative. I said they're add up to 1. So this is a convex combination. Okay, so they're aij's are non-negative and add up to 1. So basically, node I takes the look around at its neighbors, takes a convex combination of those, and subtract some step size alpha t times the subgradient of just its own local function. Okay, so gi of t is the subgradient of fi of theta. Okay, and as is normal for the analysis of the subgradient method, we are going to assume that the functions are convex. Yeah, and I said n of I is a set of neighbors. Okay, and actually you should also choose these coefficients aij should be symmetric. I'll discuss in a second how to choose it. So there's a kind of very simple idea here. The very simple idea is that you need to reconcile two things. One is that you should start pulling in the direction of your own, of the minimizer of your own function, right? That's basically sort of what adding a subgradient term does. On the other hand, what you should also be doing is you should be going in the direction of your neighbors, because all of you need to converge to the same minimizer of the global functions. And what they were able to show is that basically this works. Okay, so the theorem that was shown in NEDIC-OZDAGLAR, and I'll give a more formal, precise version of it on the next slide, but for now I'll just say the theorem that they showed is that under some assumptions, like if you take the graph corresponding to the positive aij's, it's got to be irreducible and aperiodic. And this, as usual in the analysis of the subgradient method, the subgradients are bounded. Under these kinds of assumptions, this works in the sense that all the theta i's converge to the same minimizer of the function capital F. So in some sense, you can even think of it as, this is not quite correct, but you know, you keep, every node takes these subgradients steps gi, but then it feeds them through this process of repeatedly taking convex combinations. So then you actually do take into account the subgradients of the other nodes, not immediately, but as this process of repeatedly taking convex combinations over a graph kind of gets to you in some sense. Okay, so this was proved in 2009. Let me give a slightly formal version of what's on this slide that also includes a corresponding convergence time. I'm going to need a tiny bit of notation. I'm going to define the matrix capital A, which is going to stack up these aij's. You know, if there's no edge in the graph, you know, if I and j cannot communicate, if they can't send each other messages, then you set these things to be 0. Okay, so here's a little bit of a more formal version along the same lines that also gives you kind of a corresponding convergence rate. I heard somebody say something? No? Okay.
I think it's just somebody join or leave the meeting.
Oh, I see. Okay. Yeah, I'm sorry. As I was telling Yang, I don't use WebEx. So yeah, I guess I heard a noise. I thought someone was trying to ask a question. Okay, so here is like a formal version of the theorem that's from the previous slide. This wasn't quite in the original paper that started it, that started this line of research, but it more or less was, in that it quite easily followed from the analysis. So you have this matrix capital A, which stacks up these weights aij's. You choose, let's say you choose a constant step size 1 over square root of capital T, and you run this thing You run this thing for capital T steps. Okay, see there's a minor typo in the slide. I'm gonna just go ahead and fix it. Where I put a lowercase t where I should have put a capital case T. So usually when you analyze the subgradient method, what you do is you take something like the average of all the iterates, which is what is being done here. So you evaluate it, you evaluate the error not at the last iterate, but at the running average of the iterates. And so what this says is, okay, you take basically an average of every iterate at every node through the entire process. It's easy to see, you can compute that quite easily without keeping track of much information. You evaluate the function you're trying to minimize, capital F of that, minus capital F at the optimal point, and that ends up being a sum of two terms. The first term is basically the standard thing that you see in the analysis of the subgradient method. So if you open a textbook and you look at, analysis of subgradient method, you just see this thing that I'm circling with my mouse, possibly with a different constant. It's the difference between initial, where you start, and the optimal solution, a squared norm, plus an upper bound on the size of your subgradients, divided by square root of t. But here, when you're doing the network subgradient, you also get a second term. And the second term is 1 over 1 minus lambda over square root of t, where lambda is, the second largest eigenvalue of this matrix A. Okay, so A here is a matrix whose rows add up to 1. So its largest eigenvalue is 1. It's a symmetric matrix, so its eigenvalues are real. So you look at 1 over 1 minus lambda, where lambda is the second largest eigenvalue. Okay, and we usually think of this as kind of like a price of decentralization. So the performance you get from this kind of decentralized subgradient is the performance you get from the centralized subgradient, plus something that depends on the network. And so for quite a while, people were very, very happy with these results, because these results were derived in the contexts of how do we make first order optimization work in sensor networks. And so the kind of the punchline is here, well, it converges, and it converges at the same rate with time, which is to say 1 over square root of t, as the subgradient method. But if you try to apply this to some of these machine learning applications, it doesn't work. And the reason it doesn't work is that the second term, the price of decentralization, very often will just completely and utterly dominate the first term. So let me talk about how big the second term can be. Like, what is this term? Actually, it's asking that question is a little bit begging the question. So remember how this goes. So you have this distributed subgradient method where you take convex combinations with these weights aij's and you take local subgradients. So these coefficients aij's, you have to choose them somehow. Once you choose them, you stack them up into this matrix capital A, and then basically your performance depends on the eigenvalue gap of capital A. So really asking, well, how big is this? It really depends on how you choose them, right? Maybe you choose them in a particularly stupid way, it's terrible. You choose them in a nice way, it's great. So then the question is, okay, but how do you choose these aij's? So you got to choose how you average with your neighbors. Okay, well, it turns out that a lot of ink has been spilled on these questions of how you choose them. I'm just going to tell you what the optimal choice is in terms of optimizing the worst case performance, right? So if you want to do that, there's actually a very simple choice that is the best out of the entire literature on this question, which is that you should choose the weights in this way. You should choose aij to be 1 over twice the largest of the degrees of I and degrees of j. And okay, you set your AII to make things add up to 1, to make this a convex combination. So this is symmetric, obviously. It is very easy to set up in a distributed way. All you need to know is the degrees of your neighbors, which you can tell them. Unfortunately, even with this choice, which turns out to be the best, this 1 over 1 minus lambda term can be as bad as O(n) squared. It's quite easy to see if you just use the line graph or the circle graph, and it's just a very easy exercise. Like for example, the circle graph with this choice of weights becomes a circulant matrix, and you can write down its eigenvalues immediately without a lot of work. And if you think about the issue is, let's go back one slide. So this thing here is n squared, and n is the number of nodes. So that's really bad, right? Because every time you double the number of nodes, your performance gets multiplied. This term gets multiplied by 4. And as you let the number of nodes become larger and larger and larger, for sure, this term will dominate the first one. So basically, this really limits to, this actually shows that you can be hurt by parallelizing things rather than be helped. The more nodes you add, the worse your performance is. And at some intuitive level, this should kind of make sense, right? Because one of the things about these decentralized methods is they tend to suffer from some kind of sluggishness, in the sense that you're going to evaluate your gradient or your subgradient. Someone across the network evaluates their subgradient, but you evaluate it at different points, and you're relying in some sense on old information. As the information propagates through the network in these convex combinations, in some sense you're maybe learning in a very indirect sense what goes on halfway across the network, but you don't have up-to-date information of those iterates. So because of that, because you're always computing subgradients at a bit the wrong points. And it can very well be that that effect dominates, and we see that in these bounds, okay? Now you might say, okay, is this just a bound? No, here's a simulation, and this is a very simple toy problem. One of the toy problems to work, to try in this case is to compute the median. Why the median? I mean, that's a very natural test case for subgradient method, right? Subgradient method is naturally applied on a function that's not necessarily differentiable, and where the subgradients are bounded, so the natural choice is absolute value of x. And then the median is the solution to this thing, which I'm circling with my mouse. Given numbers m1 to mn, the median is the theta that minimizes the sum of the absolute values of the deviations. So here's a simple experiment I did. I generated these MIs uniformly in -10, 10, and I ran this method until everybody was within 0.1 of the true value, and then I counted how long it took. So it takes a while, right? So for 50 nodes, it's basically 10 to the 7, so 10 million updates, and every update is 50 updates across the network. So the size of the network, here is on the x-axis. So when I point to this, it's basically n equals 50 or 48 or something like that. So the point is, this is really big. It should not take that long to compute the median of a bunch of numbers if it makes sense. So this is a very simple toy example to show that this kind of network scaling can really start dominating, and you don't get any benefit from decentralization in some very simple examples. So that's kind of the issue that sets up the work that I'm going to tell you about. There's all these results on this particular scheme and its variations, and they've been studied in a number of contexts. But the problem that I want to solve is I want to develop variations on this that are actually help as you add more and more nodes to the network. Okay, so I'm gonna kind of maybe skip this slide a little bit. When I talk to experts in this area, I often get a sequence of responses, and this slide is here just to kind of preempt those responses. The experts often say, okay, but if you did something a little bit different, if you used a more sophisticated method, you could do a little bit better. And that is true, but the underlying problem still remains, which is that as you try this method that I've described and you add more nodes to the network, performance gets worse and worse and worse. You can do a few things to make it get worse at a slower rate, which I'm sort of going to skip through here. Okay, so the main things that I'm going to describe in this presentation is this. So when you analyze the performance of these methods, they're usually a sum of two things. The first thing is the performance of sort of the centralized method that has access to, every single gradient, every single subgradient at every step. And that's kind of what you want to benchmark yourself to. And then there's a second term, which is that price of decentralization. And in some cases, that second term just goes away completely. And all you have to do is you have to wait long enough for it. And so then you basically get to perform as well as a hypothetical centralized method that knows every single subgradient at every step. And I call this property asymptotic network independence just because, it's like the network is not even there. Okay, so let me state this more formally, and it'll be clear once I give you a theorem statement. So the first thing I'm going to do is I'm going to change the assumptions somewhat. So now, before, for the previous theorem, what was being assumed is that the functions were convex and the subgradients were bounded. That's kind of the standard assumptions for analysis of subgradient method. Now, what I'm going to assume is I'm just going to assume that the functions are mu strongly convex, where mu is a positive number, and the gradients are L-Lipschitz. So not only is it differentiable, but the gradients are Lipschitz. So this is also sort of a standard assumption to analyze. There's a few kind of sets of standard assumptions. That was one, this is another. But I'm going to assume that the gradients are evaluated with noise. So in particular, at every step, what you get is the ith node gets the correct gradient of its function fi on whatever its local iterate theta I is. It can query, let's say, the gradient at any point. It gets that, but it gets that corrupted by some noise. And let's say the noise has zero mean, and just to simplify things, I'm going to say variance sigma squared across the network. Okay, so in some sense, this is more difficult because I'm corrupting the gradients by noise, but also in some sense, it's easier because I'm making stronger assumptions on the functions. In particular, it's much, much stronger to assume the functions are strongly convex rather than merely convex. Okay, so before I tell you the result, let's start by asking what is the performance of just centralized regular gradient descent on a function from this class. So the standard bound, I kind of got it from this particular paper, which was definitely not the first to do this, but it was kind of one of the more Googleable ones. You can derive a number of bounds for gradient descent under these assumptions. One of them is that what you can do is you can look at the difference to the optimal point in the squared norm, and you get to bound that by sigma squared over t mu squared. So the error decays like 1 over t with iteration t. And remember, sigma squared is the variance of the noise. Mu squared is the strong convexity parameter. Okay, if you were going to write this out a little bit more explicitly, it would be this plus some term depending on the initial condition, but the term depending on the initial condition is going to decay exponentially. So actually, if you do this in the limit, this is correct. Because this decays at a slower 1 over t rate. Okay, and the way you do this is you just do gradient descent, you just on your noisy gradients, and you take step size 1 over mu t. This is the version that achieves this level of performance. Okay, now let's think about how this would work on the star graph, right? Think back to like the first slide. What if you could do the star graph? Well, if you could do that, what would happen is you would just average all the gradients. You would have n independent estimates, so your variance would just be divided by n. So if you just did the whole thing with the star graph that we began with, you would just plug in sigma squared over n here, and so you would get that. So of course, in that setting, obviously you benefit as you throw more nodes, right? The more nodes you throw, the more independent estimates of the gradient you have, the lower your variance is. But of course, that assumes this bottleneck at the center sort of is something you don't care about and you can deal with somehow. And we want to be able to replicate this kind of result, which says that you gain as you throw more nodes into the system. We want to be able to replicate it without assuming the star graph. Okay, so this brings me to the first main result. Here it is. So we consider basically the same scheme, which is the NEDIC-OZDAGLAR scheme in this setting. So node I maintains data I of t. It updates it by taking convex combinations of its neighbors. The conditions are the same as earlier. You know, these AIJs are convex. If two nodes can't communicate, that means the corresponding AIJs are 0. They're chosen to be symmetric. Then you take, you know, your local, you take okay, you add here a step size times your local noisy gradient. So what we showed is this. We showed the performance of this is upper bounded by the first term is basically the same thing that you get over the star graph. The first term is basically what you get if you were able to just take every single gradient throughout the network and just average them magically at every step. Plus the second term, which is the price of decentralization, right? And here I use the notation O and lambda to basically denote that the constant here, what's in the parentheses just depends on t, but I'm using this to denote that the constant can depend on lambda. In particular, the constant will have a 1 over 1 minus lambda in it. And because the second largest, because this eigenvalue gap, because this inverse eigenvalue gap can implicitly depend on n, I'm also going to put an n here to basically say that, okay, this can really scale with the number of nodes. But the key point is this term is 1 over t to the 1.5. So it decays faster than the natural decay rate of the system, which is 1 over t. So sort of the point is, in the limit, so to speak, the second term disappears. The second term will be negligible compared to the first. It's just what I mean when I say it disappears, just that this is 1 over t to the 1.5, and this is 1 over t. And so in the limit, you basically just get this term, and that means you basically do as well as if you're able to just magically average all the ones immediately at every step, all the gradients immediately at every step, just like on the star graph. And there's no dependence here on the network, obviously. That's why I call it asymptotic network independence. And you can significantly generalize this to handle things like also message losses, delays, asynchronicity, and so forth. I don't really want to go into that very much. Okay, so here's a simple example of how this works in practice. We're gonna, we tried it on an SVM. So on an SVM, you know, you take a very simple example. Here's orange points. Here is blue points. You take a linear classifier to just separate them. You know, all we did in this example is we made them overlap a little bit. So what you do is you look for omega and gamma such that xk transpose omega plus gamma has the same sign as yk. You take hinge loss to measure the distance here. I guess I don't define it on the slides. What's a hinge loss? Hinge loss means it's 0 if something's above 1, and then it grows linearly if it's below 1. So it basically just says that, okay, as long as this number, that this product is above 1, the hinge loss evaluates to 0, and otherwise it grows linearly in the distance from 1. And crucially, you add a regularizer because for us, our theorem only applied to strongly convex functions. So because there's no strong convexity here, we put it in the regularizer. You distribute this data among 50 nodes on a cycle, and then you run the algorithms, and here's what you see. So centralized is orange, distributed is blue. And of course, centralized is better than distributed, and it's especially better at first. But the point is that distributed catches up. So if you look at it not, you know, after 1,000 iterations, but after, let's say, 10,000 iterations, they basically overlap. And these curves, you know, are the uncertainty curves. I forget how many runs we did. I think something like 100 runs. These begin to overlap as well. So kind of if you're going to do this many operations, it actually makes no difference. Okay, there was a question. Let me just, does your theorem require differentiability of the loss function? Yes, it does, because the assumption, let me go back to the theorem statement. Yeah, so not only does it need to have a gradient, it needs to have a Lipschitz gradient. Yeah, okay, I kind of see why you're asking this, because the hinge loss is not differentiable. Right. We took a smooth version of the hinge loss in this example. Okay, so, right, it catches up. Here's another example where we added something like delays and 30% of the links just failed, so the messages just failed to get through. There's some tricks in distributed computation you can use to make that work, and it will still catch up. It'll just take a little bit longer to do it. So if you're doing, 20,000 iterations, then it just makes no difference if you're doing centralized or distributed. So just to clarify, the centralized here just magically gets to average all of them at every star graph, magically gets to average all the gradients at every step, right? It's the star graph situation. Distributed does not get to do it, so distributed is at a big disadvantage. Nevertheless, eventually it catches up and performs as well as centralized. Here's another one, which is asynchronous. Asynchronous basically means some nodes get to skip around. Again, there's a few tricks you can use that I'm not discussing to make it handle that scenario as well. So the point here is that not only does the theorem hold in the way I've described it, but it can also hold handle a variety of realistic problems that can occur. Okay, so this is not the first paper on the subject. Actually, there were a few papers that tried to get it earlier. For example, one notable result from 2015 showed a similar phenomenon occurs for fixed step size. For fixed step size, of course, you're not converging to the optimal solution. You're converging to some kind of distribution around the optimal solution, and then you can look at like the steady state variance of your distribution. So there were some results on that a little bit earlier. Okay, so then the question is, well, but how long does it take? I had this one term that was 1 over t, which was good, and then this other term, which was 1 over t to the 1.5, which was bad. How long does it take until the second term becomes negligible compared to the first one? You can see that these results are not terribly useful if it takes a very, very long time, because the whole point is that you should be able to match the performance of the centralized method somewhat quickly. Here's a sharp estimate for this method in terms of the spectral gap. So where we work out all the constants and all the dependence, basically if you take the performance of the centralized method that gets to magically average everything, that's this thing, and you want to make sure that the distributed method is the centralized times some constant like 2 or whatever, you need a number of iterations to be bigger than n divided by spectral gap squared. And for this method, it's optimal in that we can find examples where it's exactly this bad. But this is not a fundamental lower bound. Quite possibly there can be other examples where, other methods that maybe have lower transients. And we also find that this significantly overstates what we see in practice. So we don't have a full theory, for example, to explain those simulation results I showed you, because if you think about this on the ring graph, it's pretty easy to see that on the ring graph, the inverse spectral gap is quadratic, so basically this lower bound is n to the 5th. But the performance I showed you on the slides just a few slides ago was much better than that. Okay, I'm gonna say something just very briefly on technically what's the difference between the various results here. Like how would you prove this? Just a little bit on what it really boils down to. So the standard way to analyze these things is you look at the average of the iterates throughout the network. That's what I'm going to call theta bar. Okay, so theta bar is the average of these theta i's. And you take your equation for your local update, this kind of, where you multiply this by this doubly stochastic matrix, and then you take a step size times your gradient. The fact that AIJs are symmetric and stochastic means they're doubly stochastic, and so multiplication by a doubly stochastic matrix preserves the average. So what you can write is you can write theta bar of t plus 1 is just theta bar of t minus some step size times the average of these noisy gradients n of t. And you want to think of this as a noisy gradient descent on the function capital F. And it sort of looks like that, right? You're updating theta bar by taking a step size, And what you're doing is you're averaging the gradients of all of these functions fi. Unfortunately, you're averaging them at the wrong points. Like if you wanted to do true gradient descent, what you would do is you would evaluate all the gradients at the current iterate, which is to say at theta bar. That if the gradients were all evaluated at theta bar, this would indeed be a gradient descent in capital F. But they're not. The local gradients are evaluated at the local iterates because nobody knows theta bar. So you think of this as gradient descent with some kind of potentially adversarial type perturbation. That's how you kind of analyze it. And it's very, very sensitive to the error in the perturbations. So when you do gradient descent on a strongly convex function with step size 1/t, it's quite easy to see that in expectation, you basically shrink the distance to the optimal point by something like 1/t. Plus, you get a certain term that's something like the variance. Okay, that's where the sigma squared comes in. But then you also get this perturbation that comes from the fact that gradients are evaluated at the wrong points. Okay, so this, if you ignore this delta t, this equation is something you would just write as basically line 1 or line 2 of your analysis of gradient descent. But then you're going to add this perturbation to it. So for example, really the main contribution of what we did is to make a few arguments that show that this perturbation decays at a slightly bigger rate, a slightly faster rate than what was previously known. In particular, we were able to show that the perturbation decays at a rate of 1/t to the 2.5 here. And that really makes a huge difference. The previous work basically did not have this 0.5. The previous work was just 1/t squared. And with that kind of, if you had a 1/t squared here, the best you could do is like n to the 4/t. So there is a very big sea change depending on the right rates you can get from these perturbations from the fact that the gradients are evaluated at the wrong points. If you get it to decay faster than t squared, you get to say that the network goes away. If you just get t squared, you don't get the network is going away. Okay. Yeah. Now, let's come back to the original question. The original question is, let's change back the assumptions. So let's just go back to assuming the functions are convex, but now not necessarily smooth, and let's assume that the subgradients are bounded. So this is, again, the set of assumptions that is under which the subgradient method is typically analyzed. Okay, and let's just look at the NEDIC-OZDAGLAR scheme as I first presented it. Okay, so you're just taking convex combinations and steps times your local subgradient. So generally, you analyze this in two settings about the step size. The best step size is like 1/t. Or maybe you're going to run this method for capital T iterations, and then you take a step size, which is 1/capital T. The other setting you analyze this is you assume the step size is square summable but not summable. So assume the sum of the alpha squareds of t's is finite, but the sum of the alpha t's is infinite. And okay, 1/t does not fit into that, but 1/t is actually the best step size that gives you the best rate. So these are the two kind of main assumptions that one makes on the step size. So there's a result that I found somewhat surprising, which is that network independence occurs in 1 but not in 2. So in setting 2, if you take your step size 1/t, I can construct a sequence of examples where the network never goes away and you always get worse proportional to the number of nodes. But that never happens under the step size of in part 1. Okay, so here is here's this way. Here's a chart. So just to illustrate these results, I'm going to show you kind of what they mean when you simulate this. So here I'm simulating things on a particular example. I'm not going to tell you what it is unless you ask, but there's a particular family of graphs that I constructed that I'm going to run this method on. And here on the left, I show the step size 1/t. On the x-axis is the number of iterations. See here, it's multiplied by 10 to the fourth. And what I plot on the y-axis is not quite error, but it's error multiplied by square root of t. The reason is that the error generally decays like 1 over square root of t. So if I just plotted error, the curves would all just like they would look the same. So in order to actively differentiate the curves, you're going to take the error and we're going to multiply it by square root of t. So in other words, if the error decays like 7 over square root of t, this curve, this should converge to 7. And so on this particular family of graphs, which I'm not telling you anything about, I try 3 things. N equals 10 is in blue, n equals 110 is in orange, n equals 210 is in, I guess, cyan. And you see what happens. So when n equals 10, you basically are going to decay like, I don't know, 2 over square root of t. When n equals 110, you're going to decay like about 20 over square root of t. When n is 210, you're going to decay like 38 over square root of t. And you can actually show that this decay rate, what this will flatline at, is linear in n. And linear in n is also the inverse spectral gap of the corresponding sequence of graphs. So essentially what you see here is that you never forget what the network is. The network always affects you. It always makes things worse. The more nodes you have, the worse you are. Contrast that with, let's say, a step size like 1 over t to the 3/4, which falls into the other regime. So with this step size, the error will decay like t to the 1/4. I'm sorry, the error will decay like t to the negative 1/4. And so to make this into a constant, you multiply the error by t to the 1/4. Okay. And what you see is that, okay, they do some things in the beginning, but eventually everybody is below, let's say, 1/2. Again, I show n equals 10, n equals 110, n equals 210. So the statement here is with this step size, this illustrates the theorem, which is that with this step size, it doesn't matter what the network is, as long as you wait long enough, you will be below, let's say, 1/2 times t to the minus 1/4. So this difference between lack of network independence and presence of network independence is not really a theoretical distinction. It's something you can very well observe just by doing a simulation. Okay, I'm running out of time, so I will skip this particular slides. I'm just going to say, okay, so we tried this and did this for support vector machines. You can also do it for neural networks, and I'm showing I'm referring here to a couple of recent papers which did this. In the real world, of course, the situation is more complicated because when you're training neural networks to predict, this is on ImageNet, so you're trying to predict labels for images. Anyway, when you're doing that, you don't necessarily want to you don't necessarily care about solving your optimization problems to great precision. In fact, sometimes people employ, early stopping. They say that, okay, if you run your optimization methods for too long, it'll start to overfit. What you really care about is something like validation error or error outside of your training set. Anyway, what these couple of papers have shown is they were able to get this kind of linear improvement in performance. Performance here means training time, while maintaining the same validation error as if you ran just gradient descent on the whole data. So they did this, okay, they used 32 nodes, but every node had 8 GPUs. So actually the number of the n is at 32 times 8. So they were able, I guess that's around about 250. So they were able to speed things up by about a factor of 250. And of course, this can also be applied to other settings, things like, again, sensor networks and so forth. Okay, so kind of to summarize, the network independence property tells you that you can parallelize your method among n nodes. And the more nodes you have, the better your gradients are at every step if you're evaluating them with noise, as we discussed. And consequently, you get to solve things n times faster. And you can show this both in a theoretical sense And you can show this in a sense that in practice, you can cut your training time by a factor of n, at least for n being 250 or so, and still maintain the same performance using these methods. And this gives you a strong argument for parallelizing optimization. The point is, when you parallelize something among n nodes, you get this kind of linear improvement. You get to cut your convergence time by a factor of n. And this is known in some settings. I've described two settings in which it's known. The corresponding property, you can ask this about any set of assumptions. You make some kind of assumptions on noise, you make some kind of assumption on your function, and then you get to say, well, can distributed match centralized in this setting? As I said, one open question is the size of the transients. They seem to be a lot faster in simulation than they were in the bounds that we derived. It's not clear exactly when corresponding statements can and can't be done, and also there's no theory that handles something like generalization error. Again, if you use this to train your model, the real question is, how are you going to do it? How is your trained model going to do when you give it new data it has not seen before? So there are, for example, accounts of how models trained with SGD do with generalizations. There are not really accounts of how models trained with distributed gradient descent do as far as generalization, as far as I know it. So there's a lot of open questions, and it feels like we're just kind of barely scratching the surface of this area. Okay, and with that, I'm going to thank you for your attention, and I'm happy to answer any questions if there are any.